Hello, this is a bit of electric circuits revision and it's through the medium of multiple choice questions. So there's going to be a couple of starters and then we'll do some multiple choice questions associated with it. So the first thing you need to do is press pause and have a go at this little starter. Press play when you're ready to talk about how it works. Okie doke, so I'm going to move on to the visualizer and I'm going to just draw that original circuit, which was a single cell and a single resistor. And we're thinking about what's happening to the total voltage, the total current, and the total resistance in this circuit. And I'm just going to write the equation Vt equals It RT, which is V equals IR, Ohm's law, but I've just written total as a subscript for all of them. Now, if I add in a second resistor in series, if I'm thinking about the circuit as a whole, what I've now done is, in terms of V equals IR, I have doubled the resistance. I've increased it by 2. If they're identical, I put resistors in series, it adds up. Now, the voltage of the circuit is going to stay the same because the voltage depends on the cells that have been put into the circuit, and we've not changed that. So if I've increased the resistance by 2, the total current through the circuit is going to have to reduce by 2. It's going to halve. Now, how about if instead I add that resistor in parallel? Well, if I add resistors in parallel, I decrease the resistance of the circuit because I'm giving the electrons more paths to choose and more ways to travel, and that allows them to travel more easily because there's less of them going through each component. Now I'm going to decrease the resistance, and specifically I'm decreasing it by 2 because I've got identical resistors in parallel. If this was a 10 ohm resistor and this was a 10 ohm resistor, the overall resistance would now be 5 ohms. We'll look at why that is later on. But once again, the voltage is staying the same because I haven't changed the cells. So if I've decreased the resistance by 2, this time I've increased the current and doubled it. Now our final example is if I have 2 cells with the original circuit, like so, and I'm thinking V equals IR. Now what I haven't changed here is the resistance, because I've not altered the number of resistors. What I've done is I've doubled the voltage. Now before, because voltage is on this side and IR on the same side, if I increase one, the other has to decrease. But because V and I are on opposite sides, if I keep resistance the same, to make the sum work, if I double the voltage, I also have to double the current. Because these are directly proportional, whereas I and R are indirectly proportional. And the thing to note here is that I'm always varying the voltage or the resistance. The current is always the dependent variable. It's the thing that changes because I've changed the voltage or because I've changed the resistance. So current always is affected because something else has changed. Now let's go back to the PowerPoint there. So hopefully that's answered those questions. You're now going to have a go at some multiple choice questions. So press pause, have a go at this, and then press play when you're ready to hear the answer. Okay, so question 1, a potential difference is applied to a wire, the current in the wire. Well, we've just learned that the current depends on both the potential difference and the resistance. I can either increase the current by adding cells, or I can decrease the current by adding resistors in series, or increase it by adding resistors in parallel. So the answer to this question is C. So you're going to repeat that for question 2. This is quite a new question. It doesn't really relate to what we've just talked about there, but press pause and see what you can do. Okie doke. So question 2 is basically asking, if you have a length of wire, how does the potential difference across that wire vary with length? And this wire is uniform. This is just something to learn. Voltage is proportional to length of wire. If you double the length of the wire, you double the voltage. If you halve the length of the wire, you halve the voltage. And they are directly proportional. And for that reason, just learn it. We'll talk about why it is in a moment. V and L have a direct proportional relationship. The answer must be A. Third question. Press pause. This is now about characteristics. It's another separate topic. It's just trying to jump around things. So press pause and see what you can do. Okay, the question is essentially, what is the VI graph for a diode? Now, normally we draw IV graphs because we change the voltage of this across the component, which then varies the current through it. And for a VI graph, the diode would look like this. It would be, sorry, for an IV graph, the answer would be D. But this isn't an IV graph, it's a VI graph. So we need to reverse that, and the answer is C. Just to let you know about A and B, A would be a fixed resistor. It's a straight line, no matter if it's IV or VI. B would be a filament lamp, because if it was an IV graph, it would look like this. And therefore, when we flip it, it's a VI graph, and it looks like that. If this said IV and the shape looked like this, it would be a thermistor. Okie doke, next little starter, we're going to move on to resistivity. I want you to have a go at these questions, press pause, and when you're ready to talk through them, press play, and I will talk through them with the visualizer. Okie doke, so resistivity. The equation for resistivity equals RA over L. Although more often you'll see it in terms of resistance, which is that resistance equals resistivity times length over A. And the units of resistivity are the ohm meter, and that is how I remember which way around the equation goes, because resistance is ohms times meters squared divided by meters. So that's the equation, and the unit I've already looked at. Now, how does this link to V is proportional to length, which is a multiple choice question we just did? Well, if I look at this version of resistance, if I had a uniform wire, that means that the wire is the same area throughout the length, and it's made of the same material throughout the length, I could say that resistance is proportional to length. The longer the wire, the higher the resistance, because rho and A are constants. Now, I can also say that V equals IR. And if I'm thinking about a long piece of wire, it's automatically a series circuit. If I'm thinking about a length of wire, all the electrons have to go through all of the wire. There's no choices. So that means that I is going to be the same throughout the wire, and that means I can say that V is proportional to R. Now, if V is proportional to R and R is proportional to L, I can put these two together and say that V is proportional to L. And the final question is, what happens to the quantities in the equation if you double the diameter of the wire? So let's go back to our original equation, rho equals RA over L. Now, if I've got a wire and I change it by doubling the diameter, I'm going to change two things about the wire. I'm going to change the area, and I'm going to change the resistance. The length of the wire does not change because you are doubling the area. The length is how long it is. And the resistivity doesn't change unless you change the material of the wire. So resistivity only changes if you change the material. Length only changes if you, surprise, surprise, change the length. But the area, if you double the diameter, so 2 times the diameter, means that you've doubled the radius, and area equals pi r squared. So the new area is going to equal pi times 2r squared, which is 4 pi r squared. So the new area is going to be 4 times the original area. So if we double the diameter, we quadruple the area, and therefore, to keep the resistivity the same, we have to reduce the resistance by 4. And that makes sense. If you've got a thicker wire, it's got a lower resistance. So we quadruple the area, which would mean we would quarter the resistance. So we're going to have a question that's based on resistivity. It's a core practical. Press pause, have a go, and see what you can do. Okie doke, so they're doing the experiment here, and they want to find a graph that has a gradient equal to resistivity. So what must be plotted on the y and x axes of that graph? So if the gradient is going to be resistivity, I'm going to use this equation here. So R equals rho L over A, but I'm going to write it in terms of, I'm going to move A up. So I'm going to write resistance times area equals resistivity times length. And I'm going to try and compare this to the equation y equals mx plus c. So y equals mx plus c. Now I want the gradient to be the resistivity, and currently it is. They're matching up. There's no intercept, so that can just stay as it is. So that means that y must be RA and x must be L. So let's see if that works for any of the answers. X is L, y is RA. The answer is D. Okay, next bit of thought. You're going to press pause and try and answer these questions before I explain them. Conduction and resistance. What do we think? Okie doke. So, first things first, what is the drift velocity equation? Well, it is this one. I equals NQVA. And we're going to define all the terms. So I is current, which is measured in amps. N is the charge carrier density, which is measured in meters to the -3. It's the number of electrons per meter cubed that are free to carry a current. Q is the charge of those carriers, and it's measured in coulombs. V is the drift velocity, it's the average speed of the electrons as they travel around the circuit, and it's measured in meters per second. And A is the cross-sectional area of the wire, and it's measured in meters squared. So, which will stay the same if you keep the material constant? So if you keep the material constant, you're not going to change N or Q. Material, the property here that's based on the material is N. The charge carrier density is the same for any object of the same material. So for example, copper has a charge carrier density, and a copper coin, a copper wire and a copper block all have the same charge carrier density, even though they have different dimensions. They also all use the electron to carry the electricity, and therefore Q will stay the same. You often see, instead of writing Q, you often see this written as an E, so I equals neither. So if you're keeping the material the same, N is going to stay the same. If you put things in series, well, the famous thing about series circuits is that the current is the same everywhere. So if you put things in series, the current needs to stay the same. And you're going to use both of these facts on your multiple choice questions in a second, which is here. So have a go at these two. Press pause, and then I'll go through them both at the same, well, not at the same time, but one by one. Okie doke. So what I'm going to do is I'm going to read this question and I'm going to write down what has changed. So I'm going to write the equation, and you'll see all this in a moment. I can't write and you see it at the same time. I'm going to write I equals NQVA, but I'm going to write 1 and 2 at the end as a subscript for each letter. So I'm going to write I1 equals N1 Q1 V1 A1, I2 equals N2 Q2 V2 A2. And then I'm going to think about how they relate to each other. So I'm told that the wire is replaced with a wire of a different metal with half the charge carrier density. So that means that N2 is equal to N1 divided by 2. It's half the initial N. And also I've got the same cross-sectional area. So A is still equal to A1 equals A2. And I can also assume that it's still going to be electrons carrying the charge. So Q1 equals Q2. And they want to work out, and the new current in the wire, so I2 is equal to 2 times I1, and they want to know what V2 is. That's the question. So I can now go on to my piece of paper. You can't see it all because I've managed to, V2 equals question mark, this says. So I'm going to sub in all of these N2s, A2s, I2s into the original I1 equation. So I now know that I2, actually no, I'm going to do the other way around, all the ones into here. So I2, I know, equals 2 times I1, and that's going to equal N2, which is N1 over 2, times Q2, which is the same as Q1, so that's a multiply, times V2, which is what I'm looking for, and times A2, which is the same as A1. So I'm going to bring this 2 up. I'm going to get 4I1 equals N1 Q1 V2 A1. You can't see that because I've not moved the visualizer. There we go. And I'm going to write this in terms of V2. So V2 equals 4I1 over N1 Q1 A1. I'm also going to write this initial equation in terms of V1. V1 equals I1 over N1 Q1 A1. And then if I look at this bit, that is exactly the same as this. So I can write that V2 equals 4V1. So the answer for this one is 4V. Next question, question 6. The diagram shows a current I flowing through a sample of material of length L and cross-sectional area A. Drift velocity is V. If the area and length are both double but the current remains the same, the drift velocity will be what? So I'm going to do the same thing again. I1 equals N1 Q1 V1 A1. I2 equals N1 Q1 V1. No, I2 equals N2 Q2 V2 A2. And I'm now going to think about area and length. So the length makes absolutely no difference because it's not in the equation, so we can ignore that. the area is doubled, so A2 equals 2 times A1, and I'm told the current stays the same, so I2 equals I1, and I want to know what the drift velocity is going to be. Okay, and I've kept the material the same. So if I've kept the material the same, that means that N1 equals N2 and Q1 equals Q2. So I'm going to write I2, which is equal to I1, equals N1 Q1 V2 times 2A1. So the only thing that's different here is the V2. Let's rearrange that in terms of V2 equals I1 over N1 Q1 A1. I'm going to put the 2 here. And if I rearrange this equation in terms of V1 equals I1 over N1 Q1 A1. Now let's compare these two again. So this is the same as this, which means that V1 equals V2 over 2, or V2 equals 2V1. Okay, so if I double the area, I'm going to double the velocity, which means, if I can get back onto this, we are looking for C. Okay, and then question 7, press pause while you're doing it, and then press play when you're ready to go through the answer. Okay, so the potential difference is applied across the ends of the conductor. The drift velocity is V. What is the relationship between the two? Well, I know that I equals NQVA. So I know that I is proportional to drift velocity if N, Q and A are constant. And now let's think about I. V equals IR. Therefore, I equals V over R. So I could write that V over R equals NQVA, or that V equals R NQVA, and resistance N, Q and A for a certain wire are going to stay fixed, which means that V is proportional to V. Or I could say that I is proportional to V from here, and if I is proportional to little v, they must be proportional to each other. So we are looking for C. Okay, we're going to carry this on with metallic conductors now. So have a go at these questions, press pause and then press play when you're ready to go through it again. Okie doke. So, as temperature increases for a metallic conductor, what happens? So as temperature increases, we find that the lattice ions vibrate with a higher frequency and larger amplitude, and this causes more collisions for conduction electrons. Now that reduces the current, or it slows them down, which reduces the current. And that's because if I think about I equals NQVA, if I'm slowing them down but I haven't changed the material or the fact of the electrons or the area of the wire, but I'm making them go slower, I've got to change the current, and it's got to be reduced. Now, V equals IR, and if I think about a standard circuit here, okay, I haven't changed the voltage of the circuit, I've not added anything in, so voltage stays where it is. If current has reduced, that must mean that resistance has increased. So I'm going to therefore write resistance increases. Okay, so that's essentially answered all of these questions here. In terms of this simple circuit, it doesn't change the voltage, but it does increase the resistance and therefore decreases the current, or vice versa. So let's have a go at some questions to do with that. Questions 8 and 9 are here. Press pause and then press play when you're ready to hear the answers. So question 8 is directly related to what we just talked about. So which of the following increases when the temperature of a metallic conductor increases? The amplitude of the vibrations of the lattice ions, yes. The distance between collisions definitely gets smaller. The drift velocity decreases, and the number of conduction electrons per unit volume stays the same. So the answer for question 8 is A. Question 9 is a bit of a potential divider question, and I'm just going to quickly draw it out so it's on the page for when I turn over, but I'm going to draw it with a slight difference. So here it is. I've split that up into X, Y and Y, Z. So I've made this piece of wire act as two resistors in parallel, and I want to know what the potential is across X, Z. Oh, I've done that wrong then. Sorry, let me just rewrite those numbers. This is X, Z, and then this is Y, Z. or Zy, but yeah, Zy, we'll cope. Okay, I want to know what this potential is. Now I'm going to use the potential divider equation, which is that V2 equals V in times R2 over R1 plus R2. And V2 is always the thing that you're measuring, the voltage that's out. So this is V2, which means that this must be R2 and this is R1. And V in is V0 here. So I can rewrite that equation as V0 times R2, which was XZ, divided by XZ plus YZ. If I go back to the question here, XZ plus YZ is going to be the same as XY. So instead of writing that, I can write V0 XZ over XY. And V0 XZ over XY is B. Okay. Right, carrying on and extending it, instead of looking at metallic conductors, we're now going to look at semiconductors. So same questions again, press pause as you work that out, and we'll see how we go. Okie doke, so a semiconductor, if we understand band theory, we've got a valence band where electrons usually live, and we've got a conduction band, and the electrons need to jump up to the conduction band for a semiconductor to be able to conduct. And there is an energy gap between them, but it's quite small. And if it is warm, if it's hot, so as temperature increases, there are more IR photons, infrared photons, for electrons to absorb and then jump up to the conduction band. Now let's think about how this affects the equation I equals NQVA. Okay, N is the number of electrons that are available to conduct per meter cubed. If you're suddenly increasing the temperature and letting lots of electrons jump up to the conduction band, you are massively increasing N. Now we know from the last question that when we heat things up, we also get higher, the lattice ions vibrate with a higher frequency and larger amplitude, which means more collisions, which slows down the electrons. And that still happens here. However, the comparative size of the slowdown of the electrons compared to the massive, massive jump you get in terms of the number of electrons now free to conduct means that overall Q and A are staying the same. The current is going to increase because this far outweighs this. So we have that current increases because N increases. And then as V equals IR, and we've not changed the voltage of the circuit, V is fixed. If I increases, that means that our resistance decreases. And that's what we generally know about thermistors. As you make them hotter, the resistance decreases. So if we're looking at that circuit, as we increase the temperature, the voltage is staying the same, but the current is increasing, which means the resistance must decrease. So we're going to use that for some multiple choice questions. So have a go at these two. Okay, so question 10, when a semiconductor has its temperature increased from room temperature, its resistance usually decreases because the electrons are moving faster, no, they're moving slower. The lattice ion atoms vibrate with a greater amplitude, they do, but that's going to increase the resistance. The lattice ions vibrate with a smaller amplitude, they don't. The number of charge carriers per unit volume increases, yes, it's that increase in N, so the answer is D. And then question 11, an LDR and a negative temperature coefficient thermistor, that's a normal thermistor, are connected in series, which would result in the highest combined resistance. So when I have resistors in series, I add the resistance up. So I want the highest resistance situation for both LDRs and thermistors. And we have the highest resistance for an LDR in the dark, the highest resistance for a thermistor in the cold, so the answer is A. Then we get the joy of a potential divider question with a thermistor in there. So press pause and have a go and see what you can do with this one. Okie doke, so I'm just finishing drawing this into my little paper, just so I can look at it at the same time. Okay, so we're saying what happens as we increase the temperature to the 3 meters. So as I increase the temperature, what I will find is that the resistance of the thermistor will decrease. The resistance of the fixed resistor will stay the same, but that means the total resistance, which equals R therm plus R fixed, will also decrease. I can't read that, I'll just move it over. Because if this decreases and we're adding these two together, overall the total resistance decreases. Now if you think about the whole circuit, Vt equals It RT, the total resistance of the circuit decreases, but the voltage of the circuit isn't changing, it's staying the same, which means the total current of the circuit is going to increase. So the ammeter will have an increased reading. Now the voltage thing is more difficult when we look at these two things in series. The voltage across each of these is a proportion share of the battery voltage, and it depends on how hard this is to get through. Now if I've decreased the resistance of X, that means it's now easier to get through it. So if it's comparatively easier to get through it than before, it will take less voltage to get through it. But we need to know that the total voltage equals Vx plus Vy, because it's a series circuit, and the total voltage hasn't changed. So if I've made it easier and therefore decreased the potential difference across X, I must increase the potential difference across Y to make that work. So Vx is decrease, Vy is increase, and ammeter is increase. So we've got decrease, increase, increase. The answer must be B. Okay, final section. We're looking at very quickly resistors in series and parallel. What are the rules for each? Jot them down, then press pause and then press play to listen. Okay, so in series, we've got that the total resistance is equal to R1 plus R2. Just add them up. But in parallel, we have 1 over RT, and don't forget that 1 over, equals 1 over R1 plus 1 over R2, and so on. So we're going to use that now to have a go at 2 multiple choice questions. Here they are. Press pause and then press play when you're ready to go through them. Okay, so the first question is a derivation for the resistors in series equation. She writes the steps but doesn't justify them. Which one is justified using the conservation of charge? Well, if we think about charge, we're thinking about current, because charge is current. Well, current is charge per time, so it's going to be step 4. Just as a note, step 1, V equals V1 plus V2, that's going to be the conservation of energy. And then question 14, we've got our identical resistors. What is the combined resistance between P and Q? Well, the first thing I want to do is turn this arrangement into this arrangement. Now, I can work this out. 1 over 4 plus 1 over 4 equals 1 over total resistance. And that comes out as 2 over 4 equals 1 over total resistance, or that R equals 4 over 2 equals 2 ohms. You can't see the 4 over 2 there, sorry. There you go. But I could do that, or I can just know that if I put 2 resistors that are identical in parallel, then I halve the resistance. And then these are in series, so I add them up. 4 plus 2 equals 6. So the answer here is B. So that is the end of the little revision session. Hopefully that was helpful. Yeah, and that's it. Hope you enjoyed it.